Welcome to Chapter 5, Part 2, where the points are doubled, but the colors aren't. All right, try to hold off on the bad jokes in the videos. So, as we approach the Winter Olympics, say you wanted to compare maybe a downhill racer to somebody who's doing a long jump. You know, the skier that goes down that long jump and then leans forward like a psycho and soars through the air. As the ski coach, if you had two gold medalists, how could you tell which one was better? The downhill is measured in seconds, essentially, and the long jump is probably measured in meters. So how could you compare the two? Well, the introduction of the Z-score. The Z-score does something that my dad says that you can't do. Compare apples to oranges. Sorry about the scribbles. What a z-score is the distance a value is from the mean in terms of standard deviations. It's a nice standardized value. So all of those years where you've been taking standardized tests, like the SAT or the Chap or something like that, that's what we're talking about. We're talking about taking a raw score and converting it into a universal scale. So let's see how this works. Depending on whether or not we have sample statistics or population parameters, the z-score, right, the number of standard deviations, that's what z stands for, is equal to the value that you're interested in measuring, some x value, minus the mean divided by the standard deviation, or minus the sample mean divided by the sample standard deviation. Let's try one. The SAT math section is normally distributed, right, that's our n out in front, with a population parameter and standard deviation, a mean of 500 and a standard deviation of 100, meaning the average score, typical kid gets a 500 with a standard deviation, right? The average distance a value is from 500 is about 100. Well, what if you got a 575? What does that mean? Well, clearly you're above average, but what's your z-score? Well, as we see here in the calculations, your z-score is equal to your score, an x value, minus the mean divided by the standard deviation. Don't forget to treat this upper calculation here like it was in parentheses because it is an implied parentheses. So do your subtraction and hit enter, then hit divide by 100. If you don't do your order of operations correctly, you'll get a drastically incorrect answer. And you arrive at a final answer of 0.75, which means that your score is 0.75 standard deviations above the mean score. When we talk in terms of standard deviation, now we can apply a universal set of percentages and talk about what percentage of kids score above or below that 575. And anytime we standardize a population that's normally distributed like this, we can talk about people's different measurements about them in terms of percentages, like what percentage of students have a higher IQ score than yours or below yours? What percentage of adults are taller than you or less than you? Something like that. You'd be surprised at how applicable this conversation is and how integral this is to the entire course. First, let's give you a nice little easy rule to remember. Some people refer to it as the empirical rule. I prefer to just call it the 68, 95, 99, 7 rule because those are the numbers that you have to remember. And what we're saying is what percentages of the populations lie within a certain distance of the mean. So if this green line were to represent the mean of a population, well then we could go in plus or minus 1 standard deviation of a distance away. So this represents 1 standard deviation walk that way, and this is 1 standard deviation of a walk in the reverse direction. And what we're going to say is that 68% of the population lies within that. Now, if we were to look at what we have here, the Wechsler Adult Intelligence Scale, right? It follows a normal model. Intelligence is normally distributed, and it has a mean of 100 and a standard deviation of 15, mu and sigma. So the mean is 100, and then this is 115, and when we subtract, we go to 85. So what we're saying is that 68% of adults have an intelligence score of somewhere between 85 to 115. I know it's hard to believe. If you talk to some adults, you wonder, is this really right? So what I've done here, and you might want to take a minute and copy this down, is I've just added in the others. So when I go 2 standard deviations in either direction, we're talking about 2 of these. 2 15s is 30. So when you add that to one side, I bump all the way to 130, and when I subtract, I go down to 70. When I add 3 15s, I go up to 45. So this is 145, and when I subtract that from 100, I go down to 55. So now we can say, well, 95% of the population has an adult population has an IQ score somewhere between 70 and 130, and 99.7% has an IQ score of somewhere between 55 and 145. Now, we can go back to this conversation about that modified box plot or the IQR, the upper and lower fences. Back to that question again. Is 28 hours a lot of credit hours to be taking? Is $422 a lot to be paying for that muffler? Is somebody whose IQ score is an 80, are they really that slow or not intelligent? And I think that we could start to talk about other words, maybe, words that you tend to hear hurtfully, but, what is the definition of mental retardation? What is the definition of premature baby? What is the definition of midget? These are defined terms scientifically that are just based on normally distributed populations, and once you crest past a certain point. In our course, I would say we're going to use the rule of 2. 2 sigma. Anytime you go beyond 2 standard deviations, you start to talk about, I would say, kind of weird items. So anybody who's over the threshold of 130 or under the threshold of 70 in terms of IQ scores is something that I would terminalize as unusual, or someone that's unusual with respect to their intelligence. Now we want to go back to that Chapter 5 Quiz A handout that I emailed you. And we'll go to question number 3, and it talks about adult female Dalmatians and adult female boxers. So the Dalmatians have a normally distributed weight distribution with an average of 50 pounds and a standard deviation of 3.3 pounds. And then the boxers are normally distributed as well with an average of 57.5 pounds and a standard deviation of 1.7 pounds. Okay. The question is, the teacher has 2 dogs, one of each flavor, breed, and they're both underweight. But which one of the dogs is more drastically underweight? And do you think that either of these dogs are really in any danger, I guess would be an even bigger question. So how do we decide? Well, one thing we could take a look at is we say, well, Dalmatians on average weigh less than boxers, but look at the standard deviation. Their standard deviation is larger than the boxer's standard deviation is. So there's more variability in Dalmatian weights, meaning to say that, when Dalmatians, fluctuate, it's not that uncommon for them to fluctuate in a greater capacity than boxers. Boxers have a more consistent weight. The way to do this is to compare Z-scores. The Z-score is our moneymaker. This is the standard value we will use to measure things. So go ahead and calculate the Z-score for each one. Remember, your Z-score is the value minus the mean divided by your standard deviation. So go ahead, take a minute, calculate the Z-score for each of these. And hopefully you say, wow, the boxer is drastically underweight. More than 3 standard deviations below the average weight in terms of standard deviations. That is off the charts. That boxer is malnourished, not eating, sick, something's wrong. But in terms of just answering the question, which dog is more underweight? The boxer is, because its Z-score is further from the mean. Let's just say, for instance, that the boxer was overweight by positive 3.235 standard deviations, and we were looking at an underweight Dalmatian and an overweight boxer, and we would say, which dog is more concerning? Still, the boxer is the more concerning because it is drastically overweight. So in real life, we need to take into consideration, what is it that we're really looking for? Are we comparing both under numbers? Are we comparing both over numbers? Are we comparing what's the purpose? Are we just looking for the one that's more blows my mind? Because further from the mean in either direction blows my mind. Anyway, that's that. Let's head back to the math section of the SAT again. That normal distribution with 500 points as the mean and 100 points as the standard deviation. That means, according to that 68, 95, 99, 7 rule, that 68% of students nationally that take the SAT will score somewhere between a 400 and a 500 on the SAT. But what if we wanted to know something like, what percentage of students score a 600 or less? Well, just think about this in a simple fashion. That mean is halfway. It cuts the data set right in half. So to the left of 500 is 50%. Now the two things you need to really get down about the normal distribution or the normal model is that it is symmetrical and unimodal, with the emphasis on the symmetry. That means that whatever's on this half, same mirror image over there. Again, we've talked about this. So if 68% starts from the center and works its way out, half that 68 is over here. So half of 68 is, of course, 34. So that 34% is split on both sides. Now this 34% is already included in the 50%. So all we need to do is add the additional 34. Simply stated, 84% of kids get a 600 or less. What percent get a 600 or more? Well, the other part of the 100%, 16%. And you could either say 100 minus 84, or remember this is 50, and 50 minus 34 is also 16. So it's about adding and subtracting in a very efficient manner and really thinking outside the box. I think you got enough to swallow down, most of the pie here, and you got about a little more than 50% of the material for Chapter 5. So this will be a good way to keep us from falling behind and working too quickly in class. See you guys on Monday.